Hello, we're going to do a little bit of work here with polynomials. Okay, now the polynomials, you've worked with them before. Maybe you didn't think they were polynomials. You didn't need to actually know that, but now polynomials look like this. Ax squared plus bx plus c, that's an example. We'll see lots of those. And in general, here's another one. Let's do specific examples, like say 3x to the third minus 2x plus 1, or 5x to the fourth y minus 3x squared y squared plus 2xy plus 3, for example. Now notice in this case we have only one variable. In this case, there are actually two variables. There can be more than one variable. But what you also notice about these is that they have whole number exponents. That's one thing you'll notice about them. So you have whole number exponents and no negative exponents, no fractional exponents, nothing like that. All positive whole number exponents. Now, to start off, we're going to just work with some rules for exponents. We have several rules for multiplying bases that are the same. So when we have like bases. Now, what is a base? Well, bases, and when you have an expression like this, a to the n, the a is the base relative to that exponent. So the exponent is the n value up here. So that's your exponent. Sometimes it's called a power. Okay, exponent or power. So we're going to look at some rules for multiplying some of these. Let's take some examples. Let's say we have a 3 to the third and we multiply that by 3 to the second. Well, our exponential notation, by the way, which I'm assuming people are aware of, means that we have a times a times a dot 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 a, and that you have n factors of a. That's what the notation represents. Exponential form, expanded form. Okay, this is expanded, and this up here is the exponential form. Okay, now, so over here, what we really have are, we have 3 3s here, and then we have 2 more 3 right here. So that's a total of 5, and according to our exponential, our expanded form, that's the equivalent of the exponential form. It looks like this, 3 to the 5th. Now, what you might notice is that, hey, wait a minute, there's 3 and 2. Doesn't that just make 3 to the 3 plus 2? Yes, it does. It's not a coincidence. That 5 is the same 5 as this one, and we can get it by using an addition of the exponents. So, for example, you might have 2 powers, or 2 raised to the 5th power times 2 raised to the 3rd power. That would be simply 2 to the 8th power. It works for variables too. If you have x to the 4th times x to the 7th, that'll be x to the 11th. Okay. If you have a few things to multiply, let's say you've got x to the 3rd and a y to the 4th, multiply by x to the 1st and y to the 3rd. You simply combine the like bases. That'll be 4, and this will be 7. Combining the x's with the x's and the y's with the y's and rewriting it this way. Okay, so now it doesn't really matter how many of these different products you have, or factors within that product. Okay, another example might be 3x squared times 4x to the 7th. Well, we can put the 3 and the 4 together and make a 12, and then put the x's together and makes a 9. 2 plus 7 is 9. Okay. Now, let's continue. We have some more ideas here. Let's say you have, you're trying to, and by the way, this rule that we're using here looks like this. A to the n times a to the m is simply a to the n plus m. That's the rule. Now, let's say we have an example like this. Maybe you got 3 to the 5th power and you're dividing it by 3 to the 2nd power. Well, back in arithmetic fractions, we would expand that 3 to the 5th and we would expand this. And then we would just, you know, at our leisure, we would cancel out any 3's that matched like that. So those would cancel out, which really it means divide out. And that would leave a 1 down here. And these both turn into 1's when you divide them. These both turn into 1's. So all we have here are 3 of these 3's like that, which we know is 3 to the 3rd. Well, you might be wondering, hey, is there a shortcut for this? Yes, there is. The shortcut works this way. We just take that 5 and that 2 and make a subtraction. And we leave our answer that way, a lot shorter. So this is the shortcut. And that actually becomes a rule. If we have a to the n over a to the m, then we just write it as a to the n minus m, just like that. That's our new rule. Okay, so let's look at another example on that type of problem. Let's say we got let's say 12x to the 4th, and we have a 6x squared. Well, that would be 2, because 12 over 6 is 2. And then we have x to the 4 minus 2. And you can do that mentally also. You don't have to write it down. 2x squared would be our answer. Okay. Now let's take another example. Let's say, and these are all instructions would be simplify in this case. We're simplifying things. Let's say we have a 16x squared y to the 4th, and we're going to divide that by 8x y to the 3rd. Well, we can, since it's a single product, we could write it like this. We can have a 2 because 16 over 8 is 2. And then we would have an x to the 2 minus 1 and a y to the 4 minus 3. So we can just combine the like bases like that. This would be an x, and that would be a y, and that would be our answer. Okay. So all right, let's continue. Now, the first 2 rules, and then we have, this is our 3rd rule in here. Well, examples of the 3rd rule. Our 3rd rule would be enable us to handle expressions like this. Let's say we had a 2 to the 4th power, and then you're going to raise that up to the 2nd power. So you might be thinking, okay, do I add 4 and 2, or what do I do with the 4 and the 2? And what you can do to justify it is you can say this: 2 to the 4th times 2 to the 4th equals 2 to the 8th. And you might think, 2 times 4 is 8. Is that 8 the same 8 as that? Yes, it is. It's not coincidence. All you have to do is multiply 2 times 4 to get that 8. So this is what they call power to a power. Power to power. And when you have that, you multiply the powers. So we would have a to the m raised to the nth is a to the m n, like that, product. Okay, so another example, we might have x to the 4th raised to the 3rd. Well, that's x to the 12. If you have 2x squared raised to the 3rd, then that would be 2x squared times the 2x squared. So we end up with a 2 squared and an x to the 4th. Okay. Whoops, it's a 3. Sorry about that. I got one more in there that I need to put in. Sorry about that. We got 3 of those down in here, so I have another one, 2x to the 3rd. I missed that 3 there. There's 3 of them. So that is 2 to the 3rd with an x squared. It's 3 of them makes, I see that as a 6. So that's just 8x to the 6th. Now, I did that kind of the long way, sort of the long way, but the point is this: we could easily have just written this as such. 2 to the 3rd and x to the 6th. We could have immediately multiplied that. 3 times 1 is 3. 3 times 2 is 6. And we would have gotten that same 8x to the 6th. So I stretched it out here. It's okay. Got me the answer. But you don't have to have that same stretch on all of the problems. You can shorten it a little bit. And this is again, a illustration of this property here. Okay. Now, it's in conjunction. This author and other authors might write another property that we've used here, and it looks like this. If you have x times a y, then you're going to raise that to the n, then that's both of those powers raised to the n. So I've been kind of doing that indirectly, but we can do it efficiently. We can do it. Okay, so it's an official rule that we can use, and it'll be a shortcut for us. Okay, so here's another example. So you're going to take 3x squared y to the 4th, and you're going to raise that all to the 3rd power. Well, it'll be 3 to the 3rd, x to the 6th, y to the 12th, using multiplication. That's a 27, x to the 6th, y to the 12th. Okay, so we got that now. And let's see. I think we got most of the rules taken care of. There is, let's see, pretty much taken care of all of those. Let's look at what happens when you, let's see, we're going to complicate the problems a little bit. In other words, we're going to just kind of put in a little bit of everything. Let's say we have a 3x y to the 3rd power, and we're going to raise that up to the 5th power, and then we're going to divide that by, let's say we got a 3x squared y to the 4th. Okay, and we want to simplify this. So instructions might just say simplify, or it might say divide and simplify. Sometimes they'll say that, divide and simplify, because it is a division problem. In any case, we follow our order of operations when we can, and this is the case when we do that. So I'm going to take that numerator, and I'm going to write 3 to the 5th, x to the 5th, y to the 15th. And the reason is I needed to take care of this 5. I wanted to do that first because that's an exponent before I try to do this division in here. Before I start dividing this denominator into the numerator, I have to take care of my exponents up here. Okay, so that's the reason I'm doing it. Down here, I'm just going to write this as 3x squared y to the 4th. Now I'm ready to do my simplification rules. So I got 3 to the 4th, I have an x to the 3rd, and I have a y to the 11th. And it's how we could leave it. We might do one more simplification here. 3 to the 4th is not too large. We can write it as an 81. Just like that. Okay, so let's look at another one. Let's do one more of these. Another example here. Let's start with this. Let's say we got 2x to the 5th, y squared, and that's raised to the 3rd power, and then maybe we have a x to the 2nd, y, and that's raised to the 2nd power. Okay, so you start off, we can't do the division until we take care of those exponents, so that 3 and that 2 have to be done first. So we're going to have 2 to the 3rd, x to the 15th, y to the 6th. Down here you're going to have x to the 4th. That was a 4, got a little sloppy there. Okay, 4 and y to the 2nd. Now we can do our divisions. 2 to the 3rd is just 2 to the 3rd, so we'll write it as an 8. 15 powers of x over 4 gives 11. And y to the 6th over y squared makes y to the 4th by subtracting those exponents. And that's how we would leave our answer. Okay. Now these rules, inevitably, somebody comes up with this question. What happens if I have x to the 4th and maybe I got 5 in front of it, and I'm dividing by x to the 4th? Well, before we knew anything about exponents, we would just say, hey, can't we just cancel that x to the 4th with that x to the 4th? And the answer would be yes, you could, because they're identical factors, and we have a 5. So that became a 1, and that became a 1. Now, somebody else might say, wait a minute, isn't this supposed to be 5 with an x to the 4th minus 4, like that? Yeah, according to the rule. And isn't this supposed to be x to the 0? So what is x to the 0 now? Well, if you compare these two expressions, you realize that in order for them to be equal to each other, the x to the 0 must have been a 1. So we know this is true. So that means this x to the 0 could be thought of as a 1. So that part is a 1. Now on, anytime you see x to the 0, you make it a 1. Fact is, anytime you see anything, this is assuming, of course, that x is not a 0 itself. Okay, because 0 to the 0 really isn't defined in any meaningful way. So now let's take some examples. If you have 10 to the 0, automatically 1. Okay, x to the 4th, y to the 7th with, let's say, a 3 in front of it. You can raise all that to the 0. Guess what? It's a 1. If you have x squared plus 2x plus 7, and that's raised to the 0, it's a 1. If you have 3x to the 4th, and you want to raise that to the 0, it's a 1. If you have a 9 to the 0, it's a 1. Okay, anything to the 0 is going to be a 1. The negatives also. Negative 1 to the 0 is a 1. Okay, so just wanted to make sure you understood that last addition to our rules. Okay, so that's that's enough about that for now.